Okay, so I'm back with another screencast, and I just wanted to share with you a little bit of research I've done um, looking at resistivity and using the resistivity of copper, which is the bare wire I use, to figure out the voltage drop across that bare wire. And so the resistivity. Uh, okay, so the resistance. So this is what I was looking at. I went with the Ohm's law equation, and I tried to figure out the voltage drop using the resistance times the current to get the voltage drop. And so to find the resistance, I used the equation of resistance equals to resistivity times the length of the wire divided by the cross-sectional area. And I looked up online, copper seems to have a resistivity of 10 to the minus eighth ohm meters, approximately, times my length of my wire, which I said was about 10 centimeters, which is 10 to the minus first meters. And then I divided that by the area, which I said was 10 to the minus sixth square meters. And so that gave me a resistance of 0.001 ohms, or 10 to the minus third ohms. Now, when I plug that in, and I'm assuming my current is about 2 amps flowing through that wire, and that's a bit made up, but potentially something around there. I wouldn't think it would be much more. But anyway, 0.03 ohms times 2 amps will give me a voltage drop of about 0.06 volts. So that is a small amount. And I guess it was not noticeable on my multimeter because it was so small. And then the alligator clips, it seems that the resistance is a lot higher when we move on to look here. So the clips themselves, and what I'm talking about is, the clips, not the wire, but the clips themselves. Looking at the voltage drop from the alligator clip at B to alligator clip at C, it seems that since the resistance is higher, then I would get more of a voltage drop. And so, again, a question regarding that. One more thing I wanted to mention here is that the data I got here for the voltage drops across the battery was, straightforward and what I expected for step 7 and step 8 for that matter. So A to B, the 3 volts, 2 1.5 cell SD cells. But then I had variable readings, all negative, for the voltage drops across these other points. And that's true for both step 7 and step 8. So if I would place my multimeter ends on different points of the light bulb, say, it seemed to give me a bit different readings, which, I would think that the sum of my changes in the potential for step 7 should be -3 volts. If I sum up here all these, and they gave me about -2.5 volts, which didn't really show me, conservation, I guess, of potential difference. But step 8, I guess that was a little confusing too, because I got negative voltage drops here for B to C, C to D, and D to A. But then I got positive voltage drops for C to E, E to F, and F to D. And so when I sum all that up, it gives me a sum of about 0.2 volts when I add all those voltage drops in this region here. And so that's a bit, I guess it's interesting, but also confusing. One more thing I wanted to mention is that since the voltage drop is equal to the change in electrical energy, divided by charge, then that's telling me that across the round bulb, there's a greater energy drop or energy change than the long bulb. And also there's a bigger loss of electrical energy. That's for this one. But then here I got an opposite result. And so I'd love to talk about, that in more detail. And so I guess that's all I have this week.